Picture this. You're a high schooler working on an undergraduate level math project for over 8 months. That's what half of our senior year looked like.
And just to let you know, we were not prepared for what awaited us.
Hello everyone and welcome. My name is Mateus.
And I'm Chinedu. Today we want to show you what we've been working on from March till November.
Basically, it's a summary about the most important concepts from this book by William Wood and Robert Project about the study of imperfect circles.
Let's not talk too much about it and get straight into it.
Exactly. Let's do it.
Let's have a look at a more familiar shape first, the circle. As we all know, the unit circle is defined by this equation here. And we know that we can parameterize the unit circle by setting x equal to cosine of t and setting y equal to sine of t. You can also write this in a more fancy notation, in a vectorial notation, by setting the x and y components of a two-dimensional vector to cosine and sine of t. That is analogous. What does parametrization mean in this context? It means that a red point can wander around the unit circle perfectly. But today's video is not about circles. It's about squircles, or so-called p-circles or generalized circles. They are defined by this equation here. Absolute value of x to the power of p plus absolute value of y to the power of p equals 1, where p is greater or equal to 1. And the question that we first want to ask is, what can we set x and y equal to in order for these generalized circles to be parameterized? But first, let's have a look at what these p-circles look like in the next animation.
At the top, we have our generalized equation. Let's set p equal to 2. That's our unit circle. Now let's vary p. As p approaches infinity, our p-circle approaches a square.
Now that we know what p-circles are, let's have a look at the unit circle again and appreciate why its parametrization is what some would call perfect. Why? Because the parameter t represents three things at the same time: the arc length traveled, the angle subtended, and the sectorial area with respect to the angle. You can really pause and ponder and have a look that this animation makes sense, but we really need to understand this because when we parameterize the p-circles, we will have to parameterize by one of these aspects at the time. Let's really get a feel for that with a specific example.
In our animation, you've seen how the unit circle has been parameterized by arc length, area, and angle. Remember that the parameter t is a value between 0 and 2 pi, which, when being plugged into this equation, will satisfy the equation. For an example, we picked the angle pi over 3, and we want to show how the three types of parametrization are connected to the parameter t. The angle is the easiest one to show, since it's a value between 0 and 2 pi, for which we know that it satisfies the equation. So we can say theta equals t. For the arc length, which is the distance from here to the point, we used the formula of arc length traveled. Here, 2 pi cancels out, leaving us with r times theta. Because we're in the unit circle, this is 1 times theta, so equals theta. Since theta equals t, we can say this. For the area, we use the formula of the sectorial area, which is the shaded part on here, and r squared is 1, pi cancels out, leaving us with theta over 2 or t over 2. So this would be here.
Again, let's look at the generalized equation of the p-circle, for which we know that if we set p to 2, we get the unit circle. Before, we've set x and y in terms of t to parametrize the unit circle. Now, let's use a different approach, the CIVP, coupled initial value problem. The CIVP is a system of differential equations with initial conditions given. For the unit circle, this is x of 0 equals 1 and y of 0 equals 0, which is this point here. The solution of a differential equation is one or more functions. The solution of a system of differential equations is a set of coupled functions, so functions that depend on each other. If we manage to create such a system for the unit circle whose coupled solutions are sine and cosine, then we've successfully parametrized the unit circle with this CIVP approach. Alright, let us write down this CIVP. The first thing we can write down is x of 0 equals 1 and y of 0 equals 0. This is our initial condition of the circle, and it's where the parametrization starts. And we know that cosine and sine satisfy this. So cosine of t is equal to 1 and sine of t is equal to 0 for t at 0. Now, since the solution of the CIVP should give us cosine and sine, and we know that the derivatives of cosine and sine are coupled, let us just write down their derivatives. So d dt of cosine of t is equal to minus sine of t, and d dt of sine of t is equal to cosine of t. Writing this down in a more generalized way for our CIVP gives us x prime of t is equal to minus y of t, and y prime of t is equal to x of t. This is our CIVP that serves to parametrize the unit circle. Can we write it in a way such that it applies to any p-circle?
In fact, we can. Let's see how this is done. If you look up the CIVP for any p-circle in the book, it will suggest this here. And you will see that we have kind of here an extra exponent of p minus 1 here. But why and where does this come from? Just to get a bit of intuition, plugging in 2, because when in the unit circle we were dealing with the 2 circle, you see that 2 minus 1 gives us 1, and then we get back the normal CIVP that we derived before. So it seems to work, but let's see where the rigorous proof comes from. The general idea is that when we had the unit circle, it was defined by this equation right here, and when we set x and y to the functions that parametrized it, then we got, as we know it, the Pythagorean identity. Now we are dealing with this defining equation for our p-circles. And we don't know what the functions are that parameterize them, so we just call them x of t and y of t. And that means that the equivalent equation that we would have in the p-norm would be this one here. And here it's very subtle, but the absolute values can drop because this is necessary for you to graph a p-circle in a graphic calculator. But here, because p is greater or equal to 1, it is positive anyway, and the absolute value drops for the proof anyway. So what we do is we think that if we can prove that all the points are on the p-circle for this parameterized equation, and they are in fact at a p distance 1 from this p-circle, much like all the points on a circle are at a normal distance 1 because the radius is 1, then we have proved that this CIVP is a normal and valid continuation of ours. How do we do this? We set this equal to some function g of t, and we first prove that this function is a constant, and then we say that it is precisely equal to 1. And for that proof, we use our suggested derivatives, and this should work. Well, let's just do it. Let's differentiate here. And according to the power and chain rule, this is the derivative. Bring the power down, p minus 1, and multiply by the derivative of the inside. And here you get, of course, the derivative of this function. Then we use the derivatives that we think are the natural extension from the CIVP above, and we just put them here. And then we see that something very beautiful happens. The negative sign here from this y gets put up front, and we get a negative quantity plus the same positive quantity, meaning that this side here equals to 0. And therefore, if we get that g prime of t is 0, that means that our original g was a constant. And then we can use our initial conditions to see that if we plug in g of 0, we will get that this constant is precisely 1, and it stays as 1 because it's a constant function. Therefore, if g of t is 1, we have proved it. You can read this text to see exactly the precise formulation, but basically this means that all points are at a precise p distance of 1 from the origin, and that proves that our derivatives were natural and valid extensions because we used them and we got what we wanted to get.
Now that we know the CIVP of the p-circles, we can finally parametrize the squircle, particularly the p equals 4 case, which will be the one we'll use for the rest of the video. What we did is numerically solve the CIVP via Euler's method. Let us show you a couple of animations we've constructed with it. Let's go.
Whoa, wait.
Man, Mateusz, what is this timing? You're ruining it.
No, wait, one more thing before we start. Remember when I said that the p-circles can only be parametrized by one aspect at a time, so either by area, by arc length, or by angle? Well, this is the areal parametrization, and there is a proof for it. Here's it, the page on the book, and curious viewers can have a look at it. But for now, let's just start with the animation.
You may have noticed the special notation of pi. If you haven't, then that's no problem. Anyways, this is the pi p, so a definition for pi for a specific p circle according to the areal parametrization. It is important to keep in mind that the three different types of parametrization lead to three different ways of defining pi p. In order to find the areal pi p, however, we first have to understand the connection between pi and trigonometric inverse functions and define squigonometric inverse functions.
Okay, why can we use inverse trigonometric functions to find the value of pi? This comes from a very simple idea. If you think of the sine of pi over 2, so the sine of 90 degrees, well, that's just equal to 1. And if you then take the arc sine on both sides of the equation, sine and arc sine will cancel out, and you're left with pi over 2 is equal to arc sine of 1. And if you then multiply this equation by 2 on both sides, you're left with pi is just equal to twice the arc sine of 1. Which means that if we somehow manage to find a representation of an arc sine of p, then we'll be able to calculate the value of pi p for any p circle. Let's see how this is done. For the purposes of this video, we'll only need to find arcsine p of y. and we'll need these identities on screen. Okay, the idea here is to find t as a function of y, and the first step is to differentiate according to the rules we saw in the CIVP. Then we'll recall from the fundamental equation that cos p can be written like this. We then use exponential rules to summarize the whole thing. The next step is to do a separation of variables and prepare for the integration. Integrating from 0 to t or from 0 to y on both sides leaves t alone. And that's it. That's arcsine p of y. If we now go ahead and evaluate this integral from 0 to 1, and then go ahead and multiply by 2, then this is a precise definition for the pi p-value. Specifically for the squircle that we'll use, we can plug in p equals 4 and get the numerical approximation for pi 4.
We'll keep track of all the pi p definitions that we get along the way. This is one of them. Let's add it to our list.
Okay, so we have just seen in the animation that this is a valid definition for the arcsine of p. And that means that if we evaluate this integral from 0 to 1, that's just arcsine of 1, and this should be a valid definition of pi p. If we recall that our pi is actually just the p circle with exponent 2, then we could come up with the idea to plug in 2 into this equation and see what we get. And I want to show how this is really a valid generalization. So let's do it. Okay, 2 times the integral from 0 to 1 of 1 over 1 minus u squared to the power of 1/2 du. Well, the 1/2 can be seen as a square root, therefore we could just write twice the integral from 0 to 1 of 1 over 1 minus u squared, all under the square root du. And I want to show you that this is precisely twice times arcsine of 1 or pi. Well, why? From calculus we know that the derivative of arcsine of x is just 1 over the square root of 1 minus x squared, which means that we can define the arcsine function as the integral of its derivative, because integrals and derivatives are opposites, which means that arcsine of x is just the integral from 0 to x. And remember, we now have to do a dummy variable substitution, as the integral boundary and the variable inside the integral cannot be the same. Let's just use u here of 1 over 1 minus u squared du, and I forgot the square root. And this is precisely arcsine of x, meaning that if we now replace the x with a 1, and here as well, of course, with a 1 because we're evaluating, multiply by 2 and multiply by 2, we get precisely pi. So this generalization is very valid. Plugging in 2 gives us precisely twice arcsine of 1 or pi. It's just beautiful.
Yeah, it can be beautiful. But we can go one step further. Let's have a look at special functions.
Okay, so what are these special functions and what do they have to do with Squigonometry? So here are the definitions of the beta and the gamma function. These are special functions because they have many connections. So beta and gamma are closely related to each other by this identity right here that we're going to use. And I'm not going to explain where their definitions come from. There are a lot of lovely YouTube videos that explain that. But basically the gamma function is an extension of the factorials to all the real numbers, and the beta function is a very important function in probability and statistics. The goal here is to take our pi p definition in terms of an integral and try to write it that it's very similar to the beta function integral. So let's go ahead and do that. Well, the first step that we can do is do a clever substitution. We're gonna let u to the p equals v. That means that u can be written as v to the power of 1 over p. And then from this here we can calculate our new differentiable, not du but dv, because du dv is just going to be, if we differentiate this, 1 over p times v to the 1 over p minus 1, and that means that we can just take the dv to the other side. So that's our new differentiable dv in terms of du. Very good. Also, we can recognize here that this exponent can just be written as p over p minus 1 over p, or in other words, 1 minus 1 over p. And now we're going to use these two things and rewrite our integral. That means that pi p is nothing other than 2 times the integral from 0 to 1 of 1 over 1 minus v to the power of 1 minus 1 over p times this here, 1 over p times v to the power of 1 over p minus 1 dv. Now, what we can do is we can take all the constants, so this here, up front, and then we can write this in the numerator. That means that pi p is just 2 over p times the integral from 0 to 1 of v to the power of 1 over p minus 1 over 1 minus v to the power of 1 minus 1 over p dv. And the last step is just to go ahead and write this not as a fraction, but as a product. So we're just going to do that. This part here stays the same, and then we multiply it by this here, where the exponent gets negated. So the negative 1 over p becomes positive, and the positive 1 becomes negative, dv. And if we go ahead and make our definition of the beta function be compared to this, if we compare it, then we can clearly see that, well, u and v are just being like, this is just a dummy variable replacement, right? I could have used any other letter. That's not the problem. But what is much more interesting is that this 1 over p here is playing the role of this x, and this 1 over p here is playing the role of this y, which means that pi p can be written as 2 over p times, and then this integral just becomes beta of 1 over p, 1 over p. And if you recall that identity from before, that relates gamma and beta together, that means we can just multiply and then in the denominator add, which means it becomes gamma of 1 over p times gamma of 1 over p over gamma of 1 over p plus 1 over p is gamma of 2 over p, and of course we can't forget here the factor of 2 over p, and then this here just becomes gamma of 1 over p squared. And therefore we managed to write our pi p in terms of the beta and gamma functions. Let's add that to our pi p list.
But why are there two different formulas for the same thing? Isn't that a bit unnecessary?
Well, in math, it's always very useful to have one thing be defined in two different ways. You never know what kind of connections this is going to lead to in the future. And the second point is numerical precision. Beta and gamma function are two universally known functions, and their values, even though these functions are also defined in terms of integrals and their numerical computation shouldn't be more precise, because they are very known, their values have been computed to much more precision. So if you want to find, let's say, pi 4 of the fourth circle, then you will get a much more precise result in terms of the beta and gamma function. And in fact, our book goes ahead and takes its pi p values from the right-hand definition.
Okay, that makes sense.
But I think that's enough about the areal parametrization. Let's go ahead and parameterize the squircle by its angle.
To define angular squigonometric functions, our goal is to parametrize the curve of the p-circles such that the parameter t corresponds to the angle theta. The parameter t should represent the angle from the initial point 1, 0 to any point on the curve. Let's substitute x and y in our defining equation with their polar coordinates. Then we can factor out r to the power of p. And also factor it out for both terms. We can solve for r to the power of p by dividing both sides by the terms. By taking the pth root, we can also solve for r. Let's recall our polar coordinates and substitute our new expression for r. Since we want to express data in terms of t, let us define the angular squigonometric functions sine p angular and cosine p angular of data. With these functions defined, we can now also parameterize the squircle via angle and create a sine p function that depends on the angle rather than the area.
Okay, now we are here in decimals. And why are we in decimals? Because these angular squigonometric functions, as you may have noticed by their expression and definition, can be purely expressed in terms of the normal trigonometric functions that we know, sine and cosine, which means they can be graphed totally on a graphic calculator like decimals. And as you can see here, when p equals 2, we just get the normal sine and cosine here in red and blue respectively, because this term in the denominator falls away, as p equals 2 yields here the Pythagorean trigonometric identity, and then the square root of that is of course still 1, and it gets us the normal functions. And I'm gonna put p at 4 here so that you see what these angular squigonometric functions look like for the p4 circle. And then I'm just gonna let p vary here such that you can enjoy them. Well, only because they can be purely expressed in terms of trigonometric functions doesn't mean that we won't animate them.
Unfortunately, we need the CIVP for this again. You can find this in the book on page 61. We put it here on the screen.
Exactly. And what is really happening here is that by the rigorous theorem of these CIVPs, you always need a scaling factors next to the coupled derivatives. And this scaling factor is called zeta, and in the angular parametrization, the scaling factor is precisely x of t squared plus y of t squared. If you want to have a look at that, why it's exactly that, here is the proof on screen.
But for now, let's just lay back and have a look at our animations of the angular parametrization and the squigonometric sine and cosine function. Enjoy.
But wait!
Shut up, Mateus! That was it. But we're not quite done yet. Remember how we said that there are different ways to define pi p depending on what parametrization method we choose? Well, what does it look like for pi p angular? Let's take a closer look at this, much like before, by defining angular inverse squigonometric functions.
To define angular inverse squigonometric functions, much like before, we need the CIVP and the defining equation. We'll take the derivative of the angular sine function from the CIVP and also the key equation that defines the p-circle. Remember that the derivative is a little bit more complicated here, as we presented before. The CIVP is a bit more complex. And remember that by the defining equation, we can solve for x and express it in terms of y. With all these puzzle pieces, we can proceed. We replace x of t by these expressions in the derivative expression for y of t. And then we just simplify a bit with exponent rules. The next step is to write the derivative in the Leibniz notation and then do a separation of variables. Now we can integrate from 0 to t and 0 to y. These boundaries are justified because the initial conditions are given, and voila, we have solved for t as a function of y. That's the angular arcsine of y. And again, we can evaluate this integral from 0 to 1, and first we can do the thinking of multiplying this integral by 4 and thinking, well, if we do 4 times the first quadrant, we just get a full period. That's 2 pi, which means that, much like before, 2 times this integral gives the definition of the angular pi, but that's precisely pi, because we're dealing with angles, no matter what the p-value is that we plug in here. And therefore, in the angular parametrization, the standard pi is preserved as our angular pi. This is true for any value of p.
Alright, let's add this to our list. By plugging in any value greater than 1 for p, we should always get the same value. Or as the book would say it, we have a whole family of integrals that evaluate to exactly pi. However, the numerical integration is a bit inaccurate, and even a graphical calculator won't give you the exact pi value for every p. We're now going to have a look at the last way of parametrizing the p-circle, the Arclength Parametrisation.
To define arc-length squigonometric functions and their parameter t, we'll need some concepts from calculus class, so buckle up. First of all, what is ds? ds is an approximation for the length of an infinitesimally small part of a function. Remember though, we are dealing with the p-circle. That means that we have to approximate this infinitesimally small length to the p-norm. This is how it's done. Also, you may have come across the formula for the infinitesimally small arc length ds when the curve is in parametric form. This is the generalization of this formula for the p-norm. We'll use that. Let's go ahead and write our defining equation for the squircle into its parametric form. This actually parametrizes the squircle for the first quadrant when u is between 0 and 1. And then we take the derivatives as the formula wants us to. We plug it in, and that's already an expression for ds, but we can make this look cleaner if we just go through a lot of simplifications. Now we have an expression for ds. We can use that to define pi p arc, because it should be half the circumference of the p circle, or in other words, the p arc length traveled when you go through a semi-rotation of the p circle. But you can also express this in a different way. Namely, if you take the line y equals x and take its intersection point in the first quadrant with the squircle, that point right there is also 1/4 of the semicircle. So if we work out what that point is, we can make the integral look a little more slick. Just set y equal to x and solve what this value has to be. And finally, we can multiply the integral by 4 to get a valid definition of pi p arc that we'll add to our list in a couple of moments. We can also use ds to go ahead and define the Arclength squigonometric functions. Have a read through this explanation, but we'll have a more detailed look at them in Desmos in a couple of moments. Just a few remarks here. It is very weird that these arc-length functions are defined in terms of integral boundaries, but they are the only functions that make these two forms of representing t, which remember is the p arc length traveled until a certain point, true. So it is a valid way to define them. But again, we'll have a more detailed look at them. Also, the book goes ahead and goes one step further. It uses these definitions of t to go through a more complicated proof to say that this definition for t is really valid. And he uses this to go ahead, take derivatives, and define the CIVP for the Arclength parametrization. Again, it has to deal with that scaling factor zeta, and we're not going to get into that. But here's the CIVP such that you know how we created our animations. Again, a CIVP is very important if you want to create computer-based animations. But now, let's have a look at these functions on Desmos such that we have a better understanding. We're back on Desmos here, and we want to have a closer look at these functions. So first of all, I want to emphasize that concept of the p arc length or the p distance. The distance between 2 points classically is a straight line, and it can be calculated using the distance formula. But when we are in the p norm, in our case p equals 4, then you can see that the distance or the p distance between 2 points is a different value. It gets shorter in this case. And that's what I want to emphasize. We're not dealing with classical distances here. Okay, let's have a look at the integral definitions of t. Here we have a valid parametrization for the first quadrant of the squircle. This is a parametric equation written in Desmos here. And you can see as v goes from 0 to 1, then it parametrizes this first quadrant. Okay, what can we do with this? These are the definitions of t, and you can see that I've replaced just the v here, or the c of t that you saw in the animation, with the x coordinate that we saw in the parametric expression, and the y coordinate with the parametric y expression. And you can see that both of these integrals give us the p distance traveled from this point here, 1, 0, until this point here, if the squircle were parametrized in a counterclockwise direction. It is important to note that it doesn't really matter that this parametric expression here makes the point actually go around in a clockwise direction. It's just a way to show where this point is and that these integrals will yield this arc length traveled here. What are we actually doing here? For the cosine integral, you have to think of it as an integral in x direction. So you're integrating from the x coordinate until x equals 1 in a parametric form. So it gives us this p arc length traveled. And for the sine function, we've just substituted the y coordinate in because we're integrating from y equals 0 until the y coordinate of the point. And this will also, because the function is in parametric form, give us this arc length traveled. So actually, it doesn't matter which form of this parametric equation that you have, as long as you're plugging the expression for the y coordinate in the sine integral and the expression for the x coordinate in the cosine integral. I think we now have a much better understanding of what the p arc length traveled, or t, is, and that these squigonometric functions are defined as boundaries of integrals. Very interesting. Adding also this to our list, we'll now play the corresponding animations.
Finally, dude. Yes, we're done! We've parametrized the p-circle by area, angle, and arc length. But wait, why is the video not over?
Dude, Chidu, you know what would be really fun?
What?
3D squircles!
No! Alright, how do we do this? Well, let's start with the unit circle on a two-dimensional coordinate system. By increasing the exponent from 2 to 4, we transform the circle into a squircle. Varying the semi-axis A and B creates a general hyperellipse. Higher B values stretch the shape vertically, and higher A values stretch it horizontally. And back to the squircle, which is also a special case hyperellipse, where A and B equal 1. Now let's enter the third dimension. Revolving the squircle around the x-axis creates a three-dimensional solid of revolution, which is known as a superegg. You can see the formula of the superegg here. It comes from revolving the hyperellipse around its x-axis. To stretch it into the yz direction, we increase b. To stretch it at its axis of revolution, we increase a. Now, let us look at our last shape, the superellipsoid. Unlike the superegg, it is not a solid of revolution. It has three distinct semi-axes, defined by this formula here. For simplicity, we set all exponents to 4. We can now stretch it independently along all axes. The superellipsoid provides independent control over all three dimensions, making it a more versatile geometric form than the superegg. For the next section, let's calculate the areas and volumes of these newly introduced shapes. This will involve the usage of some formulas given by the book. We're not going to prove them, but they'll be referenced. Whenever we use them, they're colored in blue. But for now, let's get into the hyperellipse. Here you have one as a simple example. Notice how the quadrants are symmetric. It's going to be important. To be able to calculate the area, we first want to solve the hyperellipse equation for y. Taking only the positive values gives us the first two quadrants of the function. Due to symmetry, we calculate the area of the first quadrant and multiply by 4. That means with integral boundaries from 0 to a. The book tells us that whenever we have such expressions, we can do these specific substitutions. With our substitution, we can find out what dt is in terms of dx. Furthermore, the term inside the radical can be simplified like this. Also, a substitution requires us to change the integral boundaries. So if we set x equal to 0 and x equal to a in our substitution, that means that sine p of t has to equal 0, respectively 1, making t equal to 0 and pi over 2. Now, we put all these steps together and we take the integral to the t world. So we substitute the new differential on the right, our simplified radical expression in the middle, and our new integral boundaries. Now we use exponent rules and take the constants out of the integral, leaving us with this, a standard Squigonometric integral, which we can use a formula in the book for. applying the formula and evaluating the upper and lower bound gives us pi p over 2. And with that, the area is precisely pi p times a times b. Now remember that the squircle is a special case of the hyperellipse, which means its area is pi p times 1 times 1, which is just pi p. That means we can take the integral for the hyperellipse area, substitute a is equal to 1 and b is equal to 1 into it, and because we know that the area is precisely pi p, we get another valid definition that will be added to our list. At last, here is a summary of all that we just did. With this third definition of areal pi p via the area of hyperellipses, our last pi p definition is here, and finally, our list of definitions is complete.
Let's go ahead and calculate the volume of a superegg. As you saw in the animation, the superegg is a standard solid of revolution, meaning that we can use the disk method to find its volume. First, we need to solve the hyperellipse equation for y like we did before, and that's going to be our radius that's going to be inserted into the formula. Again, we integrate from 0 to a and then multiply by 2 to get the full volume. Taking all the constants out of the integral, and then we perform Squigonometric substitution one more time according to the book. In a similar manner than before, we can use the substitution to find out what dt is in terms of dx. We can also again find out what the integral boundaries will be after the substitution. And here we can also simplify this term, which before was inside of a radical. Because we're raising this expression, however, to the power of 2 over p, the expression becomes just a squared times cos p of t squared. Substituting all back into the integral and pulling all the constants out and doing some cancellation using exponent rules, we can simplify the expression to only this. Now this is not quite a standard Squigonometric integral. We first have to reduce that power with the so-called reduction formula from the book. We take this formula for granted, and here m is just standardly equal to p equals 1 for this example. Calculating all the different permutations that we need in the formula, meaning 3, 2, and 1, we just insert it back to it. And don't forget, we have to evaluate this first term with the upper and lower boundary. But this term will actually be precisely 0, because at the higher boundary, cos p of pi p over 2 is 0, and at the lower boundary, sin p of 0 is 0. So this whole term falls away and we're just left with the integral. Pay attention, this is not the same integral as before. There's an exponent of p missing here, so we can't just do what we did before. We have to apply another formula from the book and relate these Squigonometric functions to the beta function again. Again, seeing what m and n would be here makes it easy to evaluate this integral. We can also write it, of course, in terms of the gamma function because of the identity that we showed earlier. So the full volume is just taking that result and multiplying of what we have before. Making it look a little bit more pretty, we have a final expression for the superegg's volume. And now, let's go ahead and calculate a specific example. There you have it. Here's a summary of what we did again, just for you to have a clear overview in your mind. At last, let's calculate the volume of a superellipsoid. First, the defining equation. And remember that we can stretch it into x, y, and z direction independently. To find out the volume of a superellipsoid, this problem setup is going to be very similar to when trying to find the volume of a ball with a triple integral. When we solve that problem, you normally convert coordinates into spherical coordinates. And that's what we're going to do. But we're going to use p-spherical coordinates. If you look at the diagram of the book on page 143, these expressions of sine and cosine become very clear for how we can express x, y, and z into this new coordinate system. Note that these parameters will make our integral boundaries later much simpler to set up, but more on that later. To determine, however, what the scaling factors for our new differentials in our new coordinate system is, we have to find the determinant of the Jacobian matrix. The Jacobian matrix is just all partial derivatives in all directions. Recall, however, that the derivative of sine p of t and cos p of t are these derivatives according to their CIVP. Now we can set up the Jacobian matrix with all its partial derivatives and calculate its determinant by the formula that you saw before. Again, we take the absolute value here because the scaling factor needs to always be positive. And now we can literally convert our problem. What was before x, y, and z is now rho, t, and u with the scaling factor that we just found out, and ABC, we can forget about that to account for the stretch. The p-spherical wedge can be now perfectly expressed in terms of the boundaries of all these parameters. And it makes a lot of sense from that diagram on page 143. Because rho is our radius, so it goes from 0 to 1, t is the first angle, and u is the second angle. Now, we can set up all our integrals and we can split them because nothing depends on each other, and calculate these three integrals individually. The first two integrals are no problem, since the first one is just a power rule and the second one was just a constant function. The third one, however, reminds us of what we did for the volume of the super egg, meaning we can apply formula 9.7 one more time. We get rid of the cosine by setting the power of cosine to be 0, and then we just get our solution again in terms of the beta and gamma functions. This is now the result for the third integral, and with that we can calculate the final volume by multiplying all the integrals together and account for the stretching factors. Putting all of it into a much nicer form, we get the volume expression for a superellipsoid. So let's do some examples. So what's the volume of a unit superellipsoid? Well, just apply the formula. And now, let's calculate one where it's stretched into x and y direction. And again, here's a summary. We determined the volume formula for a superellipsoid via setting up a triple integral and converting the coordinates into p-spherical coordinates. And then we calculated two specific examples.
Catch!
Whoa! Well, this has been quite a journey. Anyway, thank you so much for having watched our video. We hope you leave with the feeling of having learned something new.
Despite some stressful phases, it's been a lot of fun for us to work on this as our Matura project. Share the video if you found it interesting.
And finally, we hope this video has inspired many of you guys to work on their own math topics and conduct their own research. And if so, go ahead, do it like us, and just go for it. You won't regret it.
What we did is numerically solve the CIVP via Euler's... Oh my...